Besides very briefly discussing the definition of Lewis acids and bases, we've mainly only focused on Bronsted acids and bases so far this quarter. As a refresher, a Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. These are most commonly seen in transition metal chemistry. Transition metals, which are in that large middle section of the periodic table, tend to be positively charged in the aqueous phase, and therefore are lacking in electrons. The higher the positive charge, the more the metal wants electrons, and thus the more acidic that metal is. In solution, metals will wait around waiting for some electron donors to come along and share with them. When this happens, the base doesn't just stop by, donate its electrons, and leave. It will usually hang out around the metal. We call this whole group a coordination complex because the Lewis bases are coordinated around the Lewis acid. We've even given acids and bases special names in these cases, where the acid is the metal center and the bases are the ligands. Ligands can be a variety of electron donors. They're sometimes ionic, sometimes neutral, but the full list can be found in the lecture slides. As an example, let's take a look at the silver chloride complex, or AgCl2-. And you can see here that my metal center is silver, and I must have Cl- ligands around it. The whole complex has a charge of -1, and each of those chlorines contribute a -1 charge to the total. So the silver metal center must have a +1 charge. Something that's really important to know, though, about coordination complexes is that they are very likely to form in solution, as in the equilibrium of formation, like this one that I drew right here for AgCl2-, has a large equilibrium constant of Kf equal to 2.5 times 10 to the 5th. Now, usually whenever there's a large K constant, I just assume that the reaction goes to completion, hence the forward arrow here. But there will be a small amount of reactant still at equilibrium since that reverse reaction occurs. So to account for this, I always break complex ion equilibria into two parts. The first is the formation, which I pretend goes to completion, and the second is the dissociation, or the reverse equilibrium, which will only go a little bit. The reverse equilibrium has equilibrium constant Kr, which is equal to 1/Kf. You'll remember that from our manipulating equilibria chapter way back. But this is how I approach these problems. And so taking care of the first reaction, I just treat it as if it goes to completion. And then to do the second reaction, I go through a whole Rice table and use the equilibrium constant of Kr to solve for that. In chapter 23, we'll cover more about the physics involved in coordination complexes and just more about transition metal chemistry in general.